share screen. Okay, all of you can hear me? Thumbs up if you can hear me. Can hear me? Okay, very good. Rachel, and okay?
Yeah.
Okay. Because I can't see you all, so you all have to communicate with me. All right, can that's a problem with Zoom. When I cannot see, I can only see your name and Rachel is capital R and N is capital C. Okay, right. Okay, let's share screen. Where are we? Yes, kinetics was the one. So, but before we do that, we will go back to finish up the energy tutorial. Okay, where are we? Somewhere here, right? Okay, good. Okay, so last week, just to do a fast recap. So you want to have this enthalpy. This is enthalpy, this is T, this is temperature, this is entropy, remember? So ideally, we want this Gibbs free energy to be less than 0, okay, for any spontaneous reaction. Okay, so your entropy can be positive or negative depending on whether there's an increase in disorder or decrease in disorderness, right? So if it's a positive, that means your delta S, if it's positive, that means there's an increase in disorderness, okay, which is good. Okay, remember there's one negative sign here. Also, you can see that generally we always want to have a case whereby it's exothermic minus T entropy, which is positive, because that will result in this portion here. You can see my cursor. This portion here, the whole thing will end up to become a negative number, right? So negative number minus a number will definitely end up with something that is less than 0, which is ideal for a reaction that we think is spontaneous or very feasible reaction, so-called. Also, we are just using maths to illustrate, okay, how to look at your Gibbs free energy versus your enthalpy as well as your entropy, the relationship. Last week we went through all these questions. I think we ended off somewhere here, right? So now let's go on to propane. Correct or not? Because I think my marking was here. If I'm not wrong, can you all check? Is it correct? It's D, right? Hello. Everybody, correct? Is it correct? Because I think this class I stop here.
Yes. Yeah, I think it's D.
It's D, huh? Okay. Because I think I stopped my marking over here at this point before we end off the lesson last week. So should be D, Okay, can. Okay, so next one, complete combustion of propane in oxygen. So this is the equation. Okay, so equation for propane. Propane is alkane family. Okay, you learned that from O level. So you are told that this is burned completely in oxygen to form carbon dioxide and 4 water. So I write down the full structural formula. Okay, so something you all need to remember. This is called full structural formula. Okay, so in you exam you must watch out for this, or they call it displayed formula. Okay, can you write down by the side displayed formula? So these are the two terms they will ask. Okay, whether it's full structural formula or displayed formula, you have to show every single bond. Okay, so you must write like that. You see, this is called the full structural formula. So watch very carefully. Even if you have OH, you cannot put the OH together, alcohol. So you must be written as say ROH like that. Versus R group is an alkyl group, any alkyl group. This one is not. I think a common mistake is this one. A lot of students put the OH together. Cannot. Full structural formula show everything. Okay, that is very important, especially in this chapter, because we need to use the bond energy involved, right, to determine the number of bonds broken and then number of bonds formed. Then we can calculate the enthalpy. Okay, so over here you can see enthalpy, bond breaking minus your bond forming. Okay, so this is your bond forming, 4 over 4 times 2 times minus 460. Okay, so I think you all know my pattern. I really don't like this way. So let me change this to a minus, then a bracket. This one you just change to positive. Ignore the negative sign. So you just stick to what I taught you the last time round. Bond breaking, bond breaking minus bond forming. Okay, enthalpy H is VF bond breaking Okay, so your bond breaking for the reactants minus your bond forming for the product, like that. Okay, so that we ignore the sign totally. Just take from the data booklet, sub inside the formula and for use. Don't waste time. Insert the negative sign, positive sign, then end up you calculate a wrong one. Okay, so you sub that in, you solve it. I think you should be able to get this answer. Right. Can you check your calculator? I might wait for you. Try to see whether you get 1,660. If you're not calculated yet. Okay, any problem? Anyone can get the answer? And
Yeah.
okay? Okay. Then you can?
Yeah.
Okay, good. Rachel, any problem? Rachel, cannot. Okay, so remember, during exam, you are given this kind of question, draw out the full structural formula. Don't just look at it and you think that is a bond, because especially when it's written in this way, I think you all can see this is alkane. Alkene is special. Alkene, you have a double bond, so you must take the CC double bond energy instead. So the best way is to draw out, in case you make any careless mistake. Okay, so over here, draw the full structural formula. You take everything in, you can see enthalpy is less than 0. Or condition 1, remember just now we say that enthalpy usually is negative. Very good. Condition 1 is satisfied. Okay, next we look at entropy. Entropy, second condition is also satisfied, right? Because it is 4 plus 3 on the right. On the left, there is only 6. So there's an increase in total number of gas particles in the system. Okay, so more way of arranging it, therefore entropy increases. There's an increase in disorderness. Okay, so therefore the reaction is feasible at all temperature. We don't care about temperature anymore. Okay, because there's no such thing as negative your temperature for this question over here. Okay, so this condition is feasible because this is negative and then this is positive, right? So minus T times a positive number, this equation is forever negative. Oh, correct. Okay, is it true? All temperature? No. Why? Because if T can be what? Less than 0 Kelvin. Correct not? Technically, let's say negative 2 Kelvin, negative 3 Kelvin. Okay, but you must put into perspective. At negative 1, negative 2 Kelvin, that is actually 274, negative 274 degrees Celsius. Right? 274 degrees Celsius, right? Some of these reactants here, they are no longer in the gaseous form. Also, you may not even combust this thing in oxygen. Doesn't make sense. And negative, let's say negative 3 Kelvin, negative 4 Kelvin, right? You're talking about combustion in oxygen. You cannot burn something in oxygen at such a low temperature because your oxygen will freeze. Right? So even oxygen will freeze. Negative 274 degrees Celsius is very low. So this is a disclaimer, okay? Even though I say all temperature. So all temperature whereby combustion can take place, yes, this is true. Okay, so if you want to push the envelope a bit further, then you ask me, is it possible can it be negative 3 Kelvin, negative 4 Kelvin? Technically, yes, but you cannot burn something in negative 3 Kelvin oxygen. Doesn't make sense. So you must understand, so when we say at all temperature, that means at any temperature above 0 Kelvin. Okay, we are not looking at the negative Kelvin because that is too low already. The temperature is too low. It's probably below the freezing point of some of these substances here. Like for example, water. I mean, this steam, this product, it doesn't make sense, right? And negative 3 Kelvin, for example, water is already in a solid state. Also, you wonder how this reaction happen. This reaction won't happen at this kind of low temperature. So remember, and you will be looking at totally different kind of representation altogether. So this is something you have to take note, disclaimer behind this feasible at all temperature kind of relationship. All right, next. Number E. Okay, so first you have this compound over here, C8H18, and then you have C6H14 and C2H4. So there is a sigma bond involve the breaking of the stronger sigma bond in C8H18 to form the weaker pi bond in C2H4. This one is alkene, right? C2H4 is alkene. Okay, so energy is absorbed. So again, of course, you can also calculate based on what has been broken and so on. Okay, so this 230 enthalpy and 610. I think this is your CC bond. This is your CH bond, I think. So you can see the number of bonds from here to here. So there are two of them being broken. Here, see, this is C8 to C6. Okay, so you are breaking two of them, bond breaking. Okay, so bond breaking over here. So again, you just bracket this minus instead of plus. Then this one you switch to positive 610. Okay, you end up with positive 90 kilojoules per mole. Okay, energy is absorbed. Okay, if you want to use the actual value to calculate. Okay, but how about entropy? Entropy is two molecules on the right, one molecule on the left. So entropy increases. Increase the number of gas particles. Same idea to explain. So it's feasible at high temperature. You know why? Because this thing is positive now. Your entropy on the other hand is positive. But overall, if you want it to be positive, your T has to play a role. Your T has to be big and positive. Correct? In order for the second part of the equation to be a big negative number, so that your reaction is, your Gibbs free energy can be more than zero. I mean less than zero. Gibbs free energy can be less than zero only if your temperature is high enough. So that your T times your entropy overall can be a huge positive number. Then your enthalpy minus a huge positive number can end up to become a negative number. Okay, mathematically, that's why now it's high temperature. Okay, Ken? Question, any problem? Nope. Let's move on. Okay, next one. Okay, barium nitrate. This is thermal decomposition. You heat nitrate strongly, you form barium oxide, oxygen gas, and nitrogen dioxide. These are brown color gas. So this is TD. Thermal decomposition. Okay, I think last week I reminded you, this is not melting. Melting is barium nitrate melt to become barium nitrate liquid. Okay, so this is thermal decomposition, right? The whole barium nitrate actually break down to form three products. Okay, so enthalpy is zero. So decomposition process, you need energy to be taken in to break it. So this is coming from a very what you call it, qualitative angle. We know this one involve heating, so enthalpy should be zero overall. Okay, in order to break down the ionic bonds. Okay, so this is that you see a remark here. We are not expected to deduce the sign for this enthalpy. Okay, unless you are given all the lattice energy for all these compound over here. Also, if it's not, then we just need you to deduce in a very qualitative manner. Okay, of course, we can also tell you that the temperature drop at the end of the experiment. So this is a endothermic reaction, or whether the energy enthalpy temperature increase and temperature drop. Okay, so this is something that we can actually indicate. Okay, whether this reaction is endo or exo. You know, temperature drop means it's endo. You are taking in heat. The system is taking in heat. That's why before and after the temperature drop. Okay, so probably the question will tell you from 30 degrees, you end up become 10 degrees Celsius, something like that. Of course, it won't be so low. I'm just using an example. So at the end is 10 degrees Celsius. That means the temperature drop. Only reason is because that reaction is endothermic. heat enter the system, endo. Heat exit the system, exo. The word exo comes from exit. The word endo, you can remember, is entering. Okay, so temperature must drop, right? So you have to take note of the system and surrounding. If you take, I want to make it very less complicated because I know some of you, I think 3 of you don't take physics, right? So we just keep it simple. Temperature drop, that means the system taking heat. So endo. Temperature increase, the system give out heat. So it's exo. So this is endothermic. Enthalpy is greater than 0. Then your entropy is more than 0. Okay, why? Because there are 2.5 gaseous molecule on the right. On the left, there is only 0. So there's an increase in number of gaseous molecule. So therefore, entropy increases. Okay, so now let's take a look. This is positive. This one is also positive. So same scenario as E. In order for your Gibbs free energy to be less than 0, the only choice is for the temperature to be high. Correct? So therefore, if your T is high enough, the overall representation will be less than 0. Okay, any question? If I'm going too fast, let me know, or you need me to explain any part. Okay, easy. Any portion very confusing? Any part which is confusing? No? Okay, can? Shall we move on? Okay, G. Okay, G over here is your lithium solid change to lithium plus and Cl minus. So this is your hydration, right? Okay, so you can see from here gas to your aqueous and aqueous. Okay, so your enthalpy is less than 0. This is the enthalpy change of hydration involved when the ions from the ion dipole interaction is able to compensate the energy absorbed in breaking the ionic bond. Okay, so you have remember, you learn about the relationship enthalpy change of solution over here, right? Enthalpy change of solution is actually your lattice hydration energy minus your lattice energy. So you just take note, your overall in order to be soluble in water is less than 0, right? So this one is negative, this one is negative or the positive, so-called. Okay, so you have to sub in accordingly to represent your lattice energy. Okay, so your lattice energy, you can take it. Usually in your data booklet, I think they give you the forming one, right? So forming one is always exothermic. So you need to swap it inside. So you can have two, okay, whether it's plus or minus if you take it and sub it inside. Okay, so one is working against solution, the other one is working for solution. Okay, so your this the enthalpy change over here, you can see therefore is less than 0. Okay, then your entropy is more than 0. This is aqueous, so your entropy confirmed is more than 0 because on the left is solid. Okay, so when you dissolve it, enthalpy change of this chloride solid to aqueous ions, right? It will be more than 0. Okay, so there are more ways to increase, so it's feasible at all temperature. This is negative and this is positive. So definitely, no matter what happened to this T, this Gibbs free energy is always less than 0. Okay. Can Rachel, can you and N, okay?
Yep.
Okay.
Yep.
Yeah, good. Let's go on. Okay. Next part, number 10. Explain what is the term meant by entropy. So this is a measure of randomness. I think this one we went through before. Then now they ask you how the entropy will change So this is 1 mole of chlorine at 298 added to 1 mole of nitrogen at 298. So your entropy increases. So when you mix your gas particle, there are more ways of arranging it. Okay, so this entropy will increase. Positive means there's an increase in entropy. Okay, then chlorine at 298 heated to 373. So entropy is positive because the gas particles have greater energy, okay, to move. So of course, we are assuming that there's 298 Kelvin, which is 25 degrees Celsius. At room temperature, you know chlorine is already a gas. So 298 Kelvin is above the boiling point of chlorine. Also, surprisingly, when we test this question, even at internal exam paper, right, we gave 1 mole of chlorine. Some students actually ask whether is this a gas at 298. Okay, you don't need to, you have learned that from O level, right? Remember, in the elemental stage, chlorine is a greenish yellowish gas. So at room temperature 25 degrees Celsius, which is 298 Kelvin, 25 degrees Celsius, right? This is 298. So our room temperature is 25 degrees Celsius. Definitely, you are looking at chlorine gas. It cannot be chlorine liquid. So even if you don't think that is chlorine liquid or chlorine gas, right, it's still an increase in entropy, right? From a liquid to a gas is an increase in entropy. So the conclusion is still the same, but the understanding you must take note. When you describe, can you see? When you describe the thing, they are talking about gaseous particle gaining more energy, not just a change of state. A change of state from the liquid to a gaseous state, you also increase your entropy. Okay, but this one is even more severe. This is talking about a gas at room temperature being heated to 373 Kelvin, 100 degrees Celsius. So chlorine will move even faster. Oh, so this one is 100 degrees Celsius. Okay, so if you get into context, you know chlorine is a chemical weapon. So when they launch it, actually chlorine at room temperature is okay one. No? I mean, it moves. I mean, the diffusion rate is all right. Can you see that when you actually have an explosion, the condition can cause the temperature to rise. That is why chlorine becomes deadly, because it starts to move faster. That's why you see during World War I when it's being used as a chemical weapon. Initially, when it traveled to the front line, it was quite slow. Then finally, some smart person realized that if you combine it with a bomb, instead of just releasing it this way, right, together with the bomb, you pack the chlorine inside. When the thing exploded, right, the chlorine actually moved even faster, killing more people along the way. So this is why people who are good in science are dangerous people. Or they combine this entropy idea to the making of a more powerful chemical weapon. Okay, so just for appreciation. Okay, so this is the examiner report, just for your reading. Okay, number 3, chlorine react with iodine. Okay, so you form ICl3. Can you see there's one gas, there's no gaseous product that is being formed. So your entropy is negative. Okay, so you can see by now you realize a very common trend. Every time when you actually ask whether entropy increase or decrease, look for that side with more gas molecule. Confirm that will tell you whether it's an increase or decrease in entropy. Okay, so there's a decrease in gas particles, there's lesser way of arranging, therefore lower state of disorder. So your delta S must be less than 0. All very straightforward. Okay, and followed by 1000 Kelvin. 1000 Kelvin, 1 mole of chlorine is photolysis means using light to cleave. Or you all can write down there, light to cleave. You actually have seen this before. I don't know whether you can remember now. You learned that under O level at Set 4 O level organic chem, alkane substitution reaction. Can you remember? The first step involved chlorine become 2 radical. Initiation step. Can you remember? Can right? Remember? First step initiation. Initiation is photolysis. You are cutting the chlorine at the molecule into half. So you end up with 2 radicals. Radical means atom with unpaired electron. So the chlorine, right, over here you can see ClCl, the center you cut. you end up with 2 chlorine radicals. We put a dot here to represent it. Okay, so this is the same idea. So enthalpy here is increased because there's an increase in number of gaseous particles. From 1 chlorine molecule, it becomes 2 chlorine atoms. So you all must put into perspective. Both sides are gases, but now it's not just a matter of how many molecules more or less now. It is a matter of 1 molecule become 2 atoms. Therefore, the disorderness, higher state of disorderness is achieved because there are more. 1,000 molecules become 2,000 atoms now. Okay, so entropy must be positive. Okay, so just a comment here for you all to take note. So whenever you use entropy, which is more common because you want to link to the equation, you can tell me entropy change, okay, positive or negative. Then when you use the term entropy, you must tell me increase or decrease, even though they are actually talking about the same thing. Okay, so you must take note of the way you write, the terms that you're using. You cannot say enthalpy S is increasing. That's wrong. Okay, you can tell me entropy S is positive or enthalpy S, this delta S or delta S is positive or delta S is negative. Or you can tell me entropy is increasing or entropy is decreasing. They will mean the same thing, but you cannot interchange the terms. No? So that's how you answer this question. Okay, any problem before we go on to the quiz? Rachel, can you? And?
Yeah.
Yep.
Okay, good. Let's carry on. Let's go on to the quiz. We are making good progress. Okay, this is you can see on the top here, these are PJC paper. If I'm not wrong, in order for them to book P3 in front, right? These are prelim papers. You know, because for your promo paper from J1 to J2, usually they don't distribute. There are too little topics to test already. So usually they will not put in like paper 3, something like that. So you see this paper 3, these are prelim questions. 2015 PJC, Pioneer JC, prelim paper, the paper and then the question. So let's read the question for, I think you all have read already, right? So this is a context, you see? So you are, I think 2 of you are bio students, right? So you should be quite familiar with this structure. Also, you can see how they show you what is the, let me pull this aside, I cannot see the question anymore. Okay, so this is the context, and then they ask you to do a molecular formula of glucose, write a balanced equation for the complete combustion of glucose. Okay, so complete combustion give carbon dioxide and water. So you have to extract information from the question in order to help you write the equation. Okay, so let me change to red pen first. Okay, so here carbon dioxide and water, complete combustion. Okay, so that means you burn in carbon dioxide, oxygen, sorry, to form carbon dioxide and water. Okay, so you must get the equation out. Very important. Okay, because if you don't have the equation out over here, then you cannot proceed with part 2. Though. Part 2 require you to use the bond energy. So you need to know exactly how many bonds will be broken in order for you to calculate your enthalpy H. Okay, your enthalpy change, sorry, the enthalpy H or delta H. Okay, so you can see from the comment, rather than using the C double bond O, they want you to use a value for each CO bond inside your CO2. Okay, so this is what they actually ask you to do. Okay, then you can take out all the bond energy. I think these are what you will see from your data booklet, except for this one. This 805 was given in the question paper. Or you don't take the one from the data booklet. Okay, I hope you can find all the rest of them. Okay, so the number of bonds broken, CC bond, these are from the glucose, and then oxygen got 6. Also, we check. Can you double check with me? CC bond, there are 5 of them. Okay, so you can see from here. So you are trying to break 1, 2, 3, 4, 5. Well, 5 bonds. You can see, you follow my cursor. 1, 2, 3, 4, and one more 5 here. Or you must look at the screen, then you know where the 5 come from. Okay, I show you again. 1, 2, 3, 4, 5. Okay, CO bond 7 over here. CO you can see, CO 1 here, carbon join to the oxygen, there's 1 here. 1, 2, 3, 4, 5, 6, 7. Oh, 7. Okay, are you with me? Let me make it smaller. Kind of cursor cannot. Can find Can find the 7 CO bond and so on. Okay, then the OH bond there are 5. Okay, CH bond there are 7 in total. I think glucose is the more complex one. You really need to run through, but I just show you. If I look at the image, if you really cannot see the thing, then you draw the whole entire full displayed formula out. Okay, then you can see where are all the CH bonds in total. Okay, so if you really cannot see from this diagram alone, then you have to draw the whole thing out, the full structural formula. Okay, check carefully. Then after that, 6 oxygen. Oxygen is straightforward. Okay, then your CO, you must remember 1 CO2 got 2 CO bond, CO double bond. That's why times 12. Well, not 6 times 2, that is CO. This is CO2. So 12. Total 6 times 2. So it's 12. Right? Each of them got 2. Okay, OH bond is water. Water, same thing. 2 OH bond per water molecule. Total there are 6, so times 12. Okay, so once you have all the bond energy down, then I use the formula, join them together. Bond energy of your reactant minus the number of bond energy for your product. Okay, so the first part is here. Okay, the first part is here minus the rest behind. Okay, I think you can leave out this positive sign. We don't know what is it, so don't care. Actually, we don't need this positive sign. Because remember, I told you, right, eventually your negative sign will help you take care of everything. So you don't have to worry about the positive sign in front or the negative sign behind is bigger or smaller. Just take bond energy for reactant minus bond energy of product. Everything will pan out smoothly for you. Because if your energy for your product is bigger than the one in front, right, then obviously overall your calculator will show you a negative number, isn't it? Oh, so save the trouble. There's a plus here. I think it's missing. Okay, right. Give you all 1-2 minutes. Check insert all the figures in, all the number in, and calculate. Make sure you can get the answer. 764 kilojoules. If you round down, 3 significant figure is 2760 kilojoules. 36. Per mole, per mole of glucose. Huh? 2760 kilojoules per mole. 1 mole will give you 2760 kilojoules. Okay, so you can see a lot of students before they take their IPPT test, they will take what? Red Bull, chicken essence, whatever. Then I ask them why. They say they need more energy. Then you look at the calculation here, it's 2760 kilojoules per mole. Actually, you don't need to drink all those Red Bull or whatever, right? You want energy, what should you do? Take sugar, lor. Half a kg go inside you. I think you can run 20 kilometers, you also won't feel it. Okay, so try to think out of the box. Sometimes all these commercial drinks are just out to make money. Okay, everyone can make sure your calculator give you the correct value. Okay, because 3 of you are using different models of calculators, I suspect. Okay, so I do not know which model you're using. Definitely, it may be different from mine. Mine was at least 20 years old calculator. So make sure you check, save, do what you need to do. Usually I will just take 12 bond energy, this portion here, you add up already, like save inside the memory. Then you add those in front. Once you obtain those in front, those in front here, right, then you minus your memory recall. or you all know where's your memory in and memory recall button, you should get the answer. The sign will come out naturally. Negative is negative, positive that means no sign. No sign in your calculator, that means it is positive. So you must insert enthalpy. No, if you don't insert a negative sign or positive sign, it will be marked down. Okay, because this is enthalpy, not energy. Not energy, then we can go without the sign. Okay. Can Rachel, can get an answer? Negative 2760.
What does MBE means?
MBE where?
The first line.
MBE is the sum of all the bond energy.
Oh,
MBE, bond energy. Sum. This is sigma notation. Forget about the N. I don't need one. It's just I also don't know what they want this. How PJ actually teach this thing. Energy, I think Pn of sigma of the energy of the BE. Just the bond energy will do lah. BE will do. No, but the numerical figure, 3 of you can get it or not? Make sure it's doable. Okay, because I ever a candidate tell me they see this kind of question they don't want to do. No, then I ask them why, because they say I scared wrong. Then because when during normal practice they have never even tried out before. That's why they are very scared. They say wow, this one I pick up the wrong bond energy. How it's actually 12. I have only 6, so I might as well skip 2 marks. These 2 marks can decide between a A and a B. Always remember what my advice to you, okay? Because it's not a difficult question. If you know what you're doing, you just sum up everything. Even if your final answer you really get it wrong, you are given marks for your working. At least 1 out of 2 marks. Also, don't leave it blank. It's really very silly to leave it blank because this is not a difficult question. Okay. And can you manage to get the number, the figure, the value? Yeah, okay. Send you. Okay? Okay, very good. Rachel, you can get the answer. Just now you asked me you can get the answer? Negative 2760. Very good. Okay, excellent. Okay, let's go on. Okay, next one, RIJC. Okay, 2015. Paper 3, question 5. Same thing, you see? Again, they show a question like that. Okay, what do you notice? What do you notice about these two paper? Let's scroll up. Question 5. Question 5. So, in your prelim paper 3, question 5 usually is the question on thermochem. You notice the pattern is the same. All the JC happen to set at question 5. Because there's a certain order, okay, we follow the topics, okay, and so on. Okay, right. Again, can you see how is it very familiar? These two schools, they have never sit down before to talk about their prelim paper. Coincidentally, they make use of bond energy calculation. So you can see that over here, part 1 and part 2 is the same. Say they are using bond energy concept to calculate enthalpy. Okay, so let's take a look. Chemical equation. Write a chemical equation first. Write a chemical equation. This is a chemical equation given. Okay, after that, you are asked to calculate the enthalpy change or atomization of compound A. This is compound A over here. It is gaseous state. Okay, so it will take the atomization, which is your bond energy. So again, this is you can see, you can just pick out for yourself. If you cannot see, then you have to expand the whole thing out. Okay, to look carefully. Okay, so bond energy or carbon-carbon double bond, there's only one, 610. Okay, then there are 3 of them, C bond. Okay, so your CC bond, you have, where is it? 1 here, 2 here, 3 here. You see, 3 of them. Okay, you must follow my cursor. These 3 come from here. 1, 2, 3. Okay, then you have your CO bond. Okay, here you see CO bond, there are 2 of them. Very obvious, 2 of them. Plus CO bond, single CO bond is here. 1, 2. Okay, and OH bond, there are 2 here and here. Okay, so don't miss out any particular portion. Okay, then you will be able to calculate out the bond energy of it. and then you have your 4780 kilojoules per mole. Question? Don't need to add the reactant, the product, sorry. Why? There are no bonds formed here. All of them are isolated atoms. Oh, that's why you don't have the formula application is what? By right, the formula is enthalpy change, is your bond breaking BB minus BF, right? You look at this question carefully, this portion is 0. There's no bond form already, right? Enthalpy change or atomization is you actually change all of them. Okay, you atomize it, that means you change them into the elemental form, right? In the gaseous state, isolated atoms. Okay, so there's no more bonds forming. So 0. So you only focus on BB, all the bond breaking for enthalpy change or atomization. Okay, so it's 4780. I give you time, press your calculator and check. But most important thing is not just to press your calculator and check, okay? But the important thing is to know, to see for yourself where are the bonds. Okay, so like for example, there are 3 of them. Can you see from the diagram? If not, then you have to draw the full structural formula. Okay, can check your calculator. Positive, confirm positive. Bond breaking, enthalpy confirm positive. You need to take in energy in order to break. It's an endothermic reaction. Atomization will always be positive, the sign. Okay? Rachel, can you? And
Yeah.
Yes.
Yes, very good. Okay, 4780. Okay, next, construct an energy cycle to determine enthalpy change of sublimation of compound A. Can you see? Compound A sublimation. Okay, so enthalpy change, following data given to us. Enthalpy change of combustion, you have this, you have enthalpy change of vaporization, and then you have bond energy. Okay, so let's take a look. This is the proposed construction. Okay, so make sure you have all the data in. If we run through one step by step. First, you have enthalpy change of combustion of compound A. So this is the one on top. Okay, combustion of combustion is 1 mole, burn completely oxygen. Okay, so you must get used to the fact this is 2.5. It's okay. 2.5 oxygen is 5/2 oxygen. It's all right to have this. Important thing is this one must be 1 mole. Okay, because enthalpy change of combustion is always with respect to the substance we are talking about. Okay, so negative 1210. First step here. So I mark out for you first. This is first step. Okay, over here. Okay, next. Enthalpy change of vaporization, we just follow plus 40.7. Sublimation means from liquid change to gas. Okay, vaporization, water change to gas. So vaporization, 40.7. I think it's good to put the positive in front. Okay, you want to insert on your energy cycle yourself. So that when you add up, you will not add wrongly. Okay, after that, you have your 850 bond energy. I think this is 805, right? Yeah, so you have carbon CO2, but there are 4 of them. So times 2 become 8. Okay, 460, I think, is your HO bond energy. Okay, times 2, because there are 2 OH inside water. Okay, you end up with this. So far, so good. From here to here, you are actually converting all of them, your atomization of carbon dioxide and your water and your steam. Okay, this step here, change them into single atom. Okay, then you can link back to your what you're supposed to solve. This is a enthalpy change of sublimation, solid to gas. Sublimation, solid to gas. Okay, then your 4780 over here is the combustion, which is given to you in part A. Also, you can see your answer in your part 2 will be used in your energy cycle. Okay, so this is from part 2. Again, insert the sign, positive 4780 over here, or add in the sign. Then you end out at this stage, and then you from here to here, you must still join up. Because you have to observe that from here to this part here, all of them are in the single, they are yet in the single, what you call it, atom yet, right? Because you can see that from this portion, you have 2 hydrogens, 4 carbon, and 4 oxygen. Okay, so I join up with the 496, which is this oxygen here, right? The 2.5 oxygen. Okay, the OO double bond, I think, 2 to OO double bond, okay, is your 496. Okay, so then you can build the whole cycle. The whole cycle, then you can use your Hess's law. Okay, let me use a green color. Okay, so I start from here all the way here. So clockwise, anti-clockwise. Oh, like that. So you just sub everything into your Hess's law. Using Hess's law, you can substitute. You can find your enthalpy change of sublimation. Oh. Yeah, you construct first, come. Construct the cycle first, then after that insert in all the figure. Okay, convince yourself using your calculator to check. Make sure you are able to get the answer out. Question? Question? Any question? I think this question, this part here, only this portion maybe has some issue, this part here, because you may be puzzled, right? Why do we need to do this step? Can you see my cursor? This one here. Also, this part here, you need to observe, after you finish your atomization of your CO2 and water, right? Because you're making use of this data, changing them into single gaseous, right? Can you see that over here, you have 9 oxygen? So you cannot stop here, no. You stop here, you only have 4 oxygen. You cannot link from here all the way to this part. It doesn't make sense because your product is only 4 oxygen. So you must provide a bridge from the last portion here. I put a green star to this step here. Oh, the hex sign, the green star and the hex, they must link up. In order to link up, you need 5 more oxygen. That's why we need 2.5 oxygen here, so that you can link up to this stage. The rest are no problem. Carbon got 4, hydrogen got 2. Carbon got 4, hydrogen got 2. No problem. The only issue is oxygen. You are lacking oxygen from here to here. Right, the star step to the hex sign. You are short of 5 oxygen. 5 oxygen is 2.5 oxygen molecule. Well, I think that is the area a lot of time when we are doing the energy cycle, you probably get stuck there. So you need to relate the relationship between the hex one and the star one. Oh, so this one you can put a double star there. Before your promo exam, please review, because this is a unique way they want to ask this question. To start there. And Rachel, any question? Don't be shy, come. Shoot, any part?
I got no question.
No question, well, very good. Just how do you manage to, you understand from the star to the hex, is it? The hex to the star one? After I explain, or you already got it before? I mean, originally on your energy cycle,
After
you already got it.
explain.
Oh, okay. So this one is a bit unique. Oh, maybe you need, but we know lah, we know why. You see the school that said this paper, you know lah. Oh, you know what I mean. Okay, so so don't get too worried. Traditionally, maybe for year one, I usually don't set this kind of question. The star to the hex part, okay, because it's you need a bit of exposure to link up the two steps. Most students will forget about the hex to the star. They will try to loop the whole cycle down and then try to make the two the same. But if you look carefully, you'll notice it's short of 5 oxygen. So it cannot be the same step. The hex and the star cannot be the same step. So you okay? You understand the star to the hex? I need 3 of you to understand the star to the hex step. I think that is the most important. Okay, the rest, I think you all can get the info easily. So you okay?
Yeah, okay.
Now can I end there? You understand the star, the green star to the green hex? Why the additional step there, the 496 times 2.5 here? I circle this one. These 2 steps. How? Yes, which part you want me to explain again? Here, here, here. This one?
Yeah.
From here to here.
The hex.
The hex sign. Okay, so you can see from here. Okay, maybe I label them. This is 1, this is 2, this is 3. Okay, then to 4. Can you see from 3 to 4? You understand how I get 3 to 4, right? It's been dictated by the reaction. Because there are 4 here, that's why in step 3 there are 4 CO2. I need to atomize them, change them to single atom. Then you may ask me how I know I need to do that. Because in this step here in part 2, we also change them into atom. So I must make them meet each other, a common step for them to meet. Okay, but most of the time when from 3 to 4, so now you understand why from 3 to 4, I need to do that. I need to convert all the products in step 3, they become reactant, right? I need to convert them to single atom. I realized that I end up with 9 oxygen. Can you count here? 4 CO2 is 4 oxygen plus 1 oxygen. That's why it's 9. Then I observe, from part 2, right, I only have 4 oxygen. That's why I need the additional step from 5 to 4 in order to cover this gap. I need to get another 2.5 oxygen up.
So you atomize the oxygen.
Correct, yes.
Okay.
Instead of linking step 4 and step 5 together, I cannot do that. A most common problem, that they force the 4 and 5 together. So they lost this value here. 2.5 times 10, 2.5 times 496 was totally missing from the energy cycle. So this is a pretty interesting question. So for you all to see how the step 4 and step 5, how is it being done in order to make sure the whole cycle is complete. Okay, and understand? Is it better now?
Yeah.
Better now? Okay, good. Okay, 3 of you can so sub in all the values into your energy cycle, uses Hess's law. I think you can solve. Enthalpy change of sublimation is positive 170.7 kilojoules per mole. And okay, put some star. Make sure you revise for your promo exam. Okay, this question, pull it out and then look at it again, because not very typical. From 4 to 5 is not typical, not expected. Then I think your tutorial, you also never see this before. Okay, so this part here is quite an interesting way to link up the energy, all the energy terms, or to construct this energy cycle. You need to think out of the box, or to be very observant. Then you realize that you need one more step here. Okay, 4 to 5. Okay, I think this is a missing gap. Okay, from the energy cycle. Okay, let's go on. Okay, next one. This is River Valley. Okay, they plant it at paper 3, question 2C. Okay, so I don't know why they shift it to the front. Okay, but never mind. Okay, so they have process 1, process 2, process 3. Okay, the following data can be used for the subsequent question. Okay, so they give you all the enthalpy change. So you must see carefully. This is enthalpy change of formation, right? Okay, so minus 43 and so on, 45 and so on, all given to us. Okay, so now write balance equation. Okay, so you check first. Okay, balance equation is very important because in your energy cycle, you need to know exactly how many moles is being formed. Then you can draw the energy cycle, right? So you write the balance equation for process 1 and then followed by process 2. Okay, so information is given. When you are told that it's oxidized in air, definitely we are using oxygen. All the rest of the gases in the air, they are not capable of oxidizing ammonia. Okay, so don't worry about what nitrogen, argon, all these are they are unreactive gases, right? Then followed by process 2, same thing, nitrogen 4 oxide dissolve to form your nitric acid. Okay, so first, you may be surprised with the terms that's being used. How I know nitrogen oxide is nitrogen 4 oxide? Then you must remember your redox. Oxygen is -2. So inside this NO2 is +4 for nitrogen. That's why the name is nitrogen 4 oxide. Okay, similarly, I'm going to write down another one, NO, nitrogen dioxide. Okay, over here, nitrogen 2 oxide is nitrogen monoxide. Now you must get used to all these terms given at A level, because you can see that assumption is that you have mastered your redox, except for at O level, you have learned the topic on redox already. So determining the oxidation state should not be a problem to you, or should be very natural that you can tell nitrogen 4 oxide is actually NO2. Nitrogen 2 oxide is NO. Okay, so you come out with the 2 balance equation. Right? Okay, now, given that the process 2 mentioned in C is exothermic, information given to us suggests how temperature for this reaction should be controlled to maximize the yield of nitric acid. Okay, so this is actually exothermic. So what should I do? So I go back to your Gibbs free energy. Okay, so you have your Gibbs free energy. Process 2 is negative entropy, right? Because you can see from here, you have 3 on the left and 1 on the right. Okay, so therefore the entropy is already negative. So if the entropy is already negative, this factor here, right, negative T, the enthalpy S is positive. You agree with me? A negative number times a negative number is always positive. So if this is always positive, then your Gibbs free energy, what will happen to the Gibbs free energy? The lower temperature will result in a more negative enthalpy G, because this portion is negative. So in order for your Gibbs free energy to be negative, right, very much depend on T now. So you need to have a lower temperature so that this negative T delta S is a smaller positive number. Then your enthalpy over here plus the smaller positive number, right, you will end up with delta G being negative. Also reason out, slowly reason out. Even though you see what is written here, you must understand when in your mind, you must learn how to reason out. Okay, then to determine whether Gibbs free energy should be at least negative. Small negative, never mind, but should be negative in order for the reaction to be feasible. Okay. Question first, before we go on, this part here you need to understand. So you can see that in this scenario, enthalpy is negative. So just now I told you, right, the best scenario is your entropy is positive. But now in this case, your entropy is positive or negative. It's negative, right? Entropy is negative, so which is actually no good. No good for a reaction, correct? No good for a reaction, because you want the reaction to go, the more chaotic it is, the better it is. Like explosion, all these are very spontaneous and things like that. things like that, right? The whole thing very messy, suddenly increase the number of particles, or these are very spontaneous reaction. Okay, so in this case, what we can do is to control temperature. Okay, you result in a more negative enthalpy S, this delta G. Okay, right. Okay, now next 3. Now they are given the enthalpy change. You can see now they switch to calculating the enthalpy by means of an energy cycle now. Calculate a value for the enthalpy change of formation of aqueous ammonium nitrate. Okay, so we can construct. Okay, so let's try to construct. Okay, so negative 52.2 is given to us. This is the enthalpy change of formation of aqueous ammonium nitrate. Okay, so here, okay, this is the X. X is your enthalpy change of formation. Enthalpy change of formation, you must go back to your definition. It's the formation of 1 mole of the substance from their elements, right? From their elements in their standard condition, at standard condition. So at the standard condition is always O2 gas, H2 gas, N2 gas. They are not single atom. So you must fall back to the definition. That's why your definition, what I already told you, right? You need to remember your definition. You might not be tested there on them explicitly. They ask you define what is enthalpy change of formation, but the application is important because if not, you cannot come up with the correct energy cycle. Okay, then you have negative 80.8 and negative 207 over here. Yeah, I think it's from here. Negative 80.8 and negative 207. So you can see they throw a few decoy to confuse candidates. Negative 45 and negative 285 is not used in this question. Okay, so you must know what you are looking out for. Enthalpy change of formation of ammonia, 80.8, and enthalpy change of formation of nitric acid, right? So it's 207, yeah, 207. Okay, so you can solve by Hess's law. Okay, so by Hess's law, you can see, okay, green color. So from here to here is the same as from here to here. Clockwise equals to anti-clockwise. Okay, so these two are the same. Okay, follow the arrow. Follow the arrow. Okay, Ken? Any problem? Rachel? Can you? And Anne?
Yes.
Can you okay?
Yeah.
No. Rachel?
Yeah.
Can
Yeah.
So you learn something from this question. So you may ask me why they give you so many enthalpy change. Because they want to test whether you know what you are doing. That's why they give you a few decoy. You see? Enthalpy change of formation of gaseous ammonia and enthalpy change of water over here, negative 285, they are not used. Okay, so will it be possible negative 45 actually being used by a candidate? Yes. Why? Because they forget that this is aqueous ammonia. Okay, when they form your enthalpy change of solution between your ammonium nitrate, the question say is aqueous. You see? So if you did not read that part, then you will end up taking the gaseous one, negative 45, and sub in here instead of negative 80.8. Okay, that's where marks are lost. So always read the question carefully and learn how to extract the information that is useful for you. Okay, some of them are decoy. Decoy, you don't just leave it there. Don't care. You are not using. Don't be surprised. Sometimes I do experience candidates are very worried. How come I got 5 value, I only use 3? Remember, they are there to as decoy. Decoy means they are there to beef up the question. okay, to give you some kind of minefields, okay, for you to step on. Okay, so be very careful. Okay, Ken, no problem. We'll wrap up this chapter. We'll go on to kinetics. Can I check? Are you all on kinetics now? Rachel?
Yeah.
Yes. Send you? No.
Yeah.
Okay. And
Yeah.
you're all on kinetics. Very good. Okay, come. I think kinetics after that should be thermochem. Is it thermochem? Or not thermochem? What you call it? Chemical equilibrium. Okay. Never mind. We will finish our kinetics first. Okay, let's pull out this. You all have this set? Okay, all these 1, 2, 3, 4, page 2, page 3, all the way 16 pages, 23 pages in total. Okay, mine is longer than yours because mine have some other copy. I do not know where are the blanks. So if you have blanks, you let me know. I need to fill in for you or fill in along the way for you. Okay, can you all put out this copy first? Then we can start. Okay, right. Okay, before I start, let me link back to your O-level knowledge so you can see how O-level talk to A-level and then where they downplay certain concept. Okay, so the O-level you learn about factors affecting your factors affecting your, okay, write down here first. A lot of space, right? You can jot down. Factors affecting rate of reaction. Remember, you learn this, right? Okay, later then we talk about the kinetic particle theory and so on. Okay, so first you have your concentration factor. Can you remember? Concentration increases, then your particles collide with each other more often, right? Then effective collision increases, blah, blah, blah. Concentration factor, right? Then you have A, I call it area. Actually, to be right, is surface area. Surface area, you all know, usually for what? Powdered and solid, same mass. How come the powder reaction is faster? Because it has a larger surface area of contact. Okay, then after that, pressure. Pressure put a star. Pressure is for gas. Okay, so pressure higher, again, rate of reaction increases, right? So and so on. T, temperature. Can you remember? Higher the temperature, the faster the particles will move, right? Kinetic particle theory. So they'll hit each other more often. So therefore, your rate of reaction increases. So I think you all can remember this is what covered at O-level. And last one is catalyst. Catalyst is the external factor. The rest of them offer you activation energy that is what you call that, lower the activation energy, so-called. Okay, so your catalyst over here give you an alternative pathway altogether, or lower activation energy. These three, 1, 2, 3, 4, right? The first four only cause more molecules to have energy greater than the EA. The catalyst is the one that lower the EA. Okay, so later we will see in your A-level context, lower the EA. Although this one is special. Okay, it's divided into two kinds, homogeneous and heterogeneous. Okay, I don't know where you all are in your lecture. So when I bring you all through, like what I say, I try to unpack some of the concept. But along the way, when your lecturer cover again in school, right, try to combine what they have taught you and also what I've covered over here. Okay, try to make the link between what your lecturer say and what I'm going to teach you. Okay, because all of us will lecture this topic very differently. Also, certain things that I will tell you what to watch out for and so on. Okay, mine is more practical, in the sense I will tell you what are the areas that students struggle over the past and what are the important questions that will come up for this topic and so on. Also, that's my forte lah. Okay, which one is downplay? Pressure. Okay, you go and scan through all your syllabus for A-level. This pressure is downplayed because pressure and the concentration, they actually link them together. Okay, so they actually place them together. Higher pressure means higher concentration because they force more of the particles into the chamber. So they say that this is concentration factor. Also, for the time being, you just take note. Okay, how come pressure like not mentioned at all inside your A-level syllabus? It is actually there. Okay, but it's being what you call it, subsumed under concentration. Okay, because you all learn about your pressure is the particles, number of particles inside a fixed volume. So if you increase the pressure by squeezing in molecules, indirectly it's increasing the concentration of this gas inside that particular chamber. Also, these two are linked together for A level. Okay, right. Simple way to remember. Can you see? I take the first alphabet. Oh my, this box is Captain Catalyst. Oh, so this is how you remember factors affecting rate of reaction. Captain Catalyst. CAPT is short form for Captain. So that's one way to remember factors affecting rate of reaction. All right. Okay, let's go straight into the notes. Okay, so this is introduction. Okay, you all can highlight certain thing that I will talk about. Okay, then you can take note of. Okay, so remember whenever I start off with kinetic, why it come after your thermochem? Okay, because your thermochem you talk about yield, right? Why is it that you have certain yield? Why can't we have more? Why is it that your Gibbs free energy tell you it's feasible? Then we might as well try our best to get Gibbs free energy as negative as possible. So now you realize actually it's not a simple scenario, right? Because you have something called factors affecting rate of reaction. Sometimes the temperature, for example, if it's a temperature factor, right? Temperature is too low, your Gibbs free energy tell you is feasible, okay? But at the same time, you know the rate is too slow. Okay, so you have to strike a balance. Okay, the most famous chemist we are interested in is Haber. Haber process will form ammonia, right? So he actually toy around with two factors, yield, chemical equilibrium so-called, and the yield and the rate of reaction. Too slow cannot, too little cannot. So he has to toy around with all those conditions to come out with experiment with all those conditions to come out with the particular pressure and temperature. Also some story about him. Okay, so if you all read about his story, he's actually very tragic, okay, because he is a German Jewish. So and you're a history student, right? Maybe you can tell us about Haber one day also. Okay. So anyway, his story is tragic because the Germans never really trusted Haber because of the fact that he's Jewish. Okay, so they think that he will never be loyal to the Germany. So that's why he was given insufficient power in a sense, even though he's very brilliant. Okay, so in fact that is something that we are very lucky, because you can imagine if let's say they pump all the resources to Haber, I think today we will still be singing the Japanese anthem. Okay, if you all know the history, how history turned. Okay, sometimes you are actually quite lucky in the sense that because Haber was a Jew, he was not trusted, and that's why end up we have managed to, the World War II has a different ending. Okay, otherwise we may not have that kind of ending that we think that we should get. Okay, let's go into the notes for kinetics. Okay, so this is introduction. Okay, so that's what I mentioned, maximum yield in the shortest period of time with minimum cost. So this is what every chemist is talking about. Okay, so that's why you see people say your reaction too slow, speed up. Okay, or your yield too low, speed up. Okay, so you have to strike a balance. Okay, this is the introduction. Reaction rate is given by change in concentration of a substance with time. Okay, so a simple reaction A plus B. Okay, so I think this one you all know. So your rate can be your D change in A over dt. Okay, so usually it's minus because your concentration of A is dropping. Or same thing for B. So I'm not going to write for B. Okay, or you can have your concentration of C increasing with time. Okay, so one is a negative gradient, the other one is a positive gradient. Okay, you've seen that before in your rate against time curve. Okay, rate concentration against time graph. Okay, so whether you are a reactant or you have a product. Okay, so I draw here for you. Downstairs, down there don't have, right? Oh, here is here. There, all the way below. Okay, you see reactant versus your time. Okay, so negative change in reactant over delta change in time. So your dy dt you all know differentiating the change in the reactant against the change in time. That's why we call it a differential. Okay, you all learned that in maths. So for positive gradient, it's like that. This is negative gradient. This is positive gradient. Because you are forming product. You see it's going up. Okay, so this is the positive and the negative gradient accordingly. Okay, so this is how we determine the rate at any instant. Okay, if we can actually stop the reaction, we can measure all the gradients. Okay, that will tell us that the rate at every point. Okay, can you see that at the start of the reaction, the gradient is very steep? We should expect that because at the start of the reaction, right, you have a lot of reactants, very fresh. No, not fresh, okay. The reactant have not reacted yet, so you have a lot of them. Like 1000 A and 1000 B. So they collide with each other very readily. They can pair up A, B, A, B, A, B, A, B, it come out, become C, right? Okay, but as the reaction progresses, you notice what happened. Your product are blocking the remaining reactants. I use a very simple term. Okay, your solution contains a lot of C now as the reaction progresses. So your C prevent your A from hitting the B. So can you see that? That's why at the start of the reaction is always very fast, because you got a lot of reactants around. Okay, but towards the end, right, your reaction start to slow down. Eventually, the reaction stop. Okay, reaction stop. Remember, reaction stop always have this issue. A lot of students will tell me, reaction stop over here, right? Because your reactant has finished. You observe very carefully. Can you see that when this thing is horizontal, right? Your reactant have not touched zero, no? So how do we explain that? This is because this reactant is the excess reagent. Correct or not? The partner is the limiting one. That's why the reaction stop, but yet your concentration of reactant is not yet zero. Also link, try to link concept what you will have learned before in mole concept, excess reagent and limiting reagent. The graph tell you something. So don't be surprised. How come sometimes you see in your notes, the line can go all the way to zero? Then how come the curve inside this figure 1A, for example, the line suddenly stop at this point, let's say 2. I'm just using a number, just any number, 0.2 or something like that. This is trying to tell you something, no? The reaction has stopped already, but there's still reactant inside the chamber. Why? Because the partner is the limiting reagent, correct or not? So it makes sense. When the reaction stops, the reason is because there's no more reactant, but it may not be this reactant that you're talking about. This reactant is still present in excess. Okay, that's why it didn't go down to zero. But for B, maybe for example, for this question, your A in the graph is like that, figure 1A. Your B may go all the way to zero. It's okay, because B is the one that is the limiting one. Okay, so you will have reacted fully and reached all the way to zero. So I hope you understand how we relate idea between limiting reagent and excess reagent. Okay, because this one, I think most of the schools, when they teach this concept, they show the graph like that. Then reach zero already, then stop. Then this thing is still above the zero. I mean, very far away from zero, right? So how come it stopped? Because your partner got used up, or your reaction stopped. But the reaction stopped not because of this reactant. The reaction stopped because of the partner reactant. That's one reason. It's not enough. That's why the reaction stopped. Once your reactant cannot find any more partner to collide, the reaction will stop. Product is the other way around. From zero, you start going up. Can you see? Going up, initially you form very fast, right? Then you slow down, eventually you reach horizontal because your reaction stopped. Right? So you reach horizontal. Okay, so simple. Okay, let's go down to initial rate. Initial rate is obtained by drawing a tangent to the curve at t equals 0 and calculate the gradient of the tangent. Okay, later in the tutorial question, I will pull out for you because sometimes you involve two reactant A and reactant B. So they have to plot changing the concentration of one reactant. Okay, so you have a series of curve coming down. So they need to use this initial rate method in order to confirm the order of reaction with respect to the other reactant. So right now, just take note of order of reaction first at the back of your mind. Okay, later when we see the question, I will pull out for, we'll talk more about it. Okay, so for time being, just take note of initial rate. All right, so now this is the graph of the reactant against time. Okay, so you see from here. So if you want to measure the initial rate, you can also draw a tangent at this 0 point here, the tangent so-called. Okay, so you can get a gradient here. You can easily find a gradient here and a gradient here, right? So rate is inversely proportional to the reaction to be complete. So you can write here in this box, rate is inversely proportional to time. Oh, no issue, right? It's very simple. Okay, a lot of time when we cover this, a lot of students always say, I thought time more, rate is faster. Oh, it's very simple. 2.4 run, right? Those who run 9 minutes, are they faster than those who spend 20 minutes to come in? The answer is very simple, right? The shorter the time, the faster is the runner. So there is an inverse relationship here. Rate is inversely proportional to time. Oh, so you need to understand this, even though it's covered at O level before. Okay, I always find very surprising. Okay, when we talk about half-life, then you see the longer half-life, that means the faster the rate of reaction. Okay, so later we'll see what is half-life. Okay, so slowly we unpack all this concept. Okay, so what is important is this one. The gradient, the steeper the gradient is, the faster the rate. Okay, so because we are not running on the field, so now we have to relate back to your dy dt. So your steeper the gradient means the larger the value of your dy dt, for example. So the change in your y against the change in time is very rapid. That is why it's steeper. Also, you all must understand in terms of maths. I'm trying to relate some maths, your gradient like that, something like that, versus something like this. Can you see? Oh, so this is the scenario that we are experiencing. The drop in the y with respect to the time, right, is very, very fast. Oh, that's the meaning of faster the rate of reaction, the steeper the gradient. Okay, huge dy dt, so called. Okay, so gradient is 0, that means the rate of reaction is 0, same vertical already. Right, so this is where the horizontal part happened, 0 over here. Oh, okay, so reaction is stopped. Horizontal portion of the graph, that's why the gradient is 0. Okay, so this is why just now I'm trying to say, reactant get lesser and lesser, the gradient will decrease with time. Okay, now let's go to the important part. This is important. Okay, your question, right, 60% of the question for rate of reaction is this one. You will be asked to write rate equation. You will be asked to determine order of reaction. You will be asked to determine rate constant. These three you must remember. You need to be able to do for rate of reaction. 60% of the question will always be asking you on this. Okay, of course, different way of asking. Okay, so let's take a look. Rate equation is how we represent. Okay, rate is K A M M B to the power n. Order is on top. Okay, the rate constant is this small k here. Okay, so take note, small k. All right, can you take note this k over here changes with temperature and activation energy? Two factors affect k. Okay, the proportionality constant over here, k, changes with temperature and your activation energy. Order of reaction is the m and n. It must be experimentally determined. Okay, it may or may not be the stoichiometry trace coefficient. Okay, what do I mean by that? Okay, so you can circle this first. This one is very important. I need to bring to attention. For example, A plus B, right, will give you C. Okay, so this is say 2 and then 3. Okay, your rate may not be K A to the power 2, B to the power 3. Okay, this is what this statement is trying to say. Mole ratio is mole ratio. Okay, but it depends on your rate determining step. Okay, later we'll see what is the rate determining step. Okay, so you must remember this. Exam, when you're asked to balance the equation, you balance really, right? A lot of candidates always think, oh, balancing equation tell me the order of reaction really. No, there's no direct link. There's no direct link between order of reaction and the coefficient you use for your balancing, which called the stoichiometric coefficient. So you write this example here, okay? Put a star there and you use this example. I put the sign not equal, may not be equal. Sometimes coincidentally is equal. Coincidentally means that those are very simple reaction, one-step reaction. Sometimes it's the same. Okay, so that's why we use the term may or may not. You need to experimentally determine it. Okay, so the order is sum of the individual order reaction. So in this case, it's m plus n. Okay, so let's say 2 with respect to A, 1 with respect to B. So overall is 3. Question? Am I going too fast? And okay, let me adjust my earpiece. Okay, Rachel, okay? Can you? Rachel, okay? Yeah.
Why does K changes with temperature and activation energy?
The K itself, like what you said, is called the constant inside this rate equation. So this K changes with temperature because when the temperature changes, remember this is a constant. Okay, so when the temperature changes itself, right, they have proven it experimentally also that it will have a magnitude change accordingly with the temperature. Yeah, that's all you need to remember. You will not be asked to explain why. Yeah.
Oh, okay.
Okay. And next. Jenyu, any question? And yes.
Wait, so
Mm.
K is not a constant?
K is a constant at a fixed temperature. Let me put it this way. K is a constant at a particular temperature. So usually in the question paper, right, they'll tell you that this experiment is carried out at, let's say, 250 Kelvin. So your K is always the same at 250 Kelvin. But if they increase the temperature to 290, 280, your K will change the magnitude. Okay, but they will have to tell you what is the change. Okay. Yeah, or they will ask you what will change. Whether MCQ, they ask you, do you expect the K to be the same at 300 Kelvin, something like that? Yes, so you must remember your K will change with temperature.
Okay.
Okay, okay, yeah. Don't worry, when you see actual question, you know what I'm talking about. Okay, so but we now answer all these questions that you have at the back of your mind. Okay, temperature rate constant is called rate constant. It is a constant at a particular temperature. So once you change temperature, the rate constant will change. The magnitude will change. Okay?
Okay. Sorry,
Okay.
could you
Yeah.
scroll up a bit? I forgot to fill in the blanks.
Oh, sure. This one. This one?
Yeah.
Rate inversely proportional to 1 over T.
Okay.
Jenyu, any problem?
I had the same question.
Yes.
Yeah, you already answered it. So
Okay. Which question? The rate constant.
the one where K like changes with temperature.
Yeah. K is fixed at certain temperature. Okay. Okay. Second thing I want to tell you all what. Okay. Wait. And you done it?
Yes.
And you done? Okay, good. Okay, so now let me bring you down first. Okay, later you remind me about rate constant. In case I forget, I want to say something about rate constant. Okay, see whether I reach there first. Okay, can you see? Okay, now you give an example. This example like A plus B, which is what you have written here. Can you see? X may not be 1, Y may not be 2. Oh, this is what I have written here on top. So this is something that you need to take note of. Okay, so experimentally determine this is what we have. This whole equation is like that. N2O5 is 4NO2 and O2. Can you see? Rate of reaction is KN2051. It's not 2. Okay, so for appreciation, so this is something that you need to understand. Experimentally, we determine the order of reaction. Okay, so it has nothing to do with the mole ratio. Remember this figure here, this number here over here, 2, 4 is balanced by you. You actually do the balancing. Okay, so therefore it may not be the same as the order reaction. Okay, so this is order reaction, first order with respect to N2O5. Okay, so what is the order of reaction talking about? Okay, later I will explain to you what you meant by order reaction. Okay, so just for appreciation first. Example 2, can you see? Coincidentally from this equation, right? Can you see the rate equation is 1 and 1. Okay, so you have 1 mole, we have 1 mole. The order is also 1 mole, 1 and 1. Okay, so this is why I say may or may not be. So overall is a second order reaction. Okay, so your iodine does not affect you can see that your iodine over here, does not affect your order of reaction. Yeah, it's not represented inside your, what do you call that? Iodine is not represented inside rate equation. Okay, so it does not, the rate, a reaction rate is independent on the concentration of iodine. So again, is to illustrate the point that I made earlier. Okay, can you see that your balance equation, obviously it involves this substance here, CH3COCH3, reacting with iodine, correct? We know that it reacted. H plus is a catalyst, but your order of reaction tells us something very interesting. The concentration of iodine has no impact on the rate because in the whole entire rate equation, I cannot find iodine. Okay, what is the implication? What is the implication? The implication is that if you want to speed up the rate of this reaction, you don't have to worry about the concentration of iodine. You don't bother to increase the concentration of iodine because it will not help to change the order of reaction. Okay, why I want you to take note of this point? Remember, we go back to the catalyst. Just now we mentioned, right? CAPT. Correct or not? You learned that at O level. Just now I mentioned about the factors affecting rate of reaction. Can you see? This is concentration, isn't it? You look at example 2. So now you need to rewind and erase some of the information you learned before at O level. At O level, you are told that concentration increase the rate of reaction. Correct or not? Let me rephrase the term. Okay, you all can jot down somewhere. Concentration affect the rate of reaction only in the scenario it is not zero order. Okay, let me repeat again. Concentration will affect the rate of a reaction provided it is at least first order. If it's zero order, can you see here in this rate equation, I cannot find iodine. Iodine is zero order. You can actually write down if you want. You can put down iodine, the power of 0 is zero order. So anything that is zero order with respect to rate, it has no impact on the rate at all. Oh, you understand what I'm talking about? Because at O level, that time we never unpack this thing. We just tell you concentration increase, rate of reaction increase. Okay, then you all just happily, everybody answer the same way. Now you look at example 2, you realize something. The reactant is iodine. I increase the concentration of iodine, nothing happened to the rate because it is zero order. So the concentration factor, we say that is affecting rate of reaction may not be true all the time. It is only true when it's at least first order. Also, you must understand this concept that you learn at A level, appreciate it in this context of the order of reaction. Or try to recall what your O-level chemistry teacher said. Concentration factor, increase rate of reaction, then you all describe, right? Not increase particles collide more often, more effectively, therefore increase effective collision rate, rate of reaction increases. That is what you learn. Okay, but now you realize there are exceptions to the rule. There are exceptions to the concept, provided it's at least first order. If not, concentration factor may not impact the order of reaction at all. Can you see? Independent of the order of reaction. Can you highlight this? You must digest because I don't know whether when you all learn this chapter, you all know zero order, first order, second order, blah, 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 then how to determine order of reaction, your lecturer will go through. Then suddenly at the back of your mind, you remember, concentration factor. I thought concentration affect rate of reaction always. You learn that at O level, you all learn that always. The word used was always. Concentration always affect the rate of reaction. Now you know it's not true. It only affect the order of reaction. Only affect the rate of reaction provided it's not zero order. Once it's zero order, you don't care about this concentration factor already. It has no impact on the rate. Question? Thumbs up, you all, if you understand what I'm talking about. Because I need to go deep inside this concept so that you all can rewind, delete some files away from your O-level days, so that you don't get trapped inside this box. Concentration affect rate of reaction. It's not true. Oh, but if I'm going to teach this to an O-level student, they will look at me and tell me, what do you mean by zero order, first order? Then they totally blur also. Oh, but now you're at A-level, you must understand the concept of order of reaction and the implication, and then reconcile with what you learned at O-level. Then it makes sense. Or you make sense to your understanding. Okay, provided at least first order. Okay, can I example 2? Okay, now characteristic of rate constant, you see, constant will give a indication of the rate of reaction. The larger it is, the faster the rate of reaction. Okay, so this is the first factor you have to take note of. Number 1. Okay, number 2 is a constant at a particular temperature. Just now, I think, N, you also asked a question, right? So a particular temperature, your K is always constant. Okay, right. K is dependent on temperature and activation energy. So this is a factor, temperature increases. Okay, so or when a catalyst is present, your activation lowered, K will increase. Also, you only need to take note of this. Okay, simple thing, T increase, K increase. Okay, right, your EA decrease, K increase. You write down on the side. You know my style by now. Okay, when I study notes or whatever, you all need to remember shortcut, take shortcut, always do this so you have lesser thing to remember. Or don't overload your mind with a lot of unnecessary stuff. Okay, write notes. Try to summarize what this point is talking about at the back of your mind. Very useful for where? MCQ. MCQ, they will ask you, what happened when this and this happened to, what happened to K? Also, you just select temperature and EA drop, your K will increase. So your K has an inverse relationship with activation energy. This activation energy can only drop when you use catalyst. Remember just now I mentioned about Captain, right? CAPT will not impact the EA. Only catalyst will lower EA. The rest don't lower EA. The rest just result in more molecules having energy equal to EA. So you need to take note of this. These 4 of them does not affect EA. EA is only by your catalyst, alternative pathway. Okay, instead of going up Mount Everest, I give you Mount Faber, not even a mountain. Okay, so you prefer Mount Faber, right? Because it's lower than Mount Everest. You probably will finish in a couple of hours rather than spend a few months up there in the mountain, right? Right. So that is the idea of an alternative pathway of lower activation energy. Okay, right. Next, K is independent of concentration of reactant. This is important, because your reactant concentration is reflected in the rate equation. Your K is next to it. Together, they will influence the rate. Okay, your rate got 2 factors. Remember, your rate equals to K times concentration of A, the power of 1, and let's say B, the power of 1, right? About 2. Example, can you see that concentration of A, concentration of B, right? You will change the rate. Your K will also change your rate. So definitely your K is independent of these 2 concentrations. If K is dependent on these 2 concentrations, then it's no longer K. This K might as well subsume inside the concentration. Okay, so this is a simple idea to relate to and to remember. They will influence the rate. So if your K is influenced by concentration of A and B, indirectly they influence the rate, then might as well don't have K. My K can throw away. My rate equation just put down concentration of A raised to whichever power and B raised to whichever power, then your K can be thrown inside the 2 of them, the concentration of K and B, A and B respectively. Okay, next point, the units is not fixed. Okay, so write down here, not fixed. Why? Can anyone tell me why it's not fixed? Next page. Okay, so I think here don't have. Okay, let me describe here. Okay, number 1. Okay, why is it not fixed? Number 1, example, rate equals to K A the power of 1 and B the power of 1. Okay, so can you see that rate is mole per dm cube per second? Concentration is mole per dm cube. I write down in short, so it's ms minus 1 square. So therefore, your units for K units are mole per dm cube. So you can relate back here. Your K is mole minus 1 dm 3. Correct? Oh, here don't have second, sorry. Oh, so I bring this one down, right? Mole per dm cube, and then you left with your second minus 1. Can you see? Number 1, scenario 1. Okay, so different, this is a unit for first order. Second scenario, if my rate is just K and A the power of 1. Okay, so you have K will be mole per dm cube per second divided by mole per dm cube per second. So you end up with minus 1. Correct? You understand what I'm talking about? When I say it's not fixed. So your K, your rate constant units during exam, you need to determine or work out on the spot. Okay, don't assume that it's always per second or it's mole per dm cube per second. Okay, it may not be. Okay, so you have to understand this is something that you have to take note of. Work out the units of K. That's why I put down here not fixed. Oh, read. You read this whole sentence, just what I'm trying to say is not fixed. The unit is not fixed. Okay, Ken? Any question? Ken? So I go on. Okay, next one. Rate equation can only be determined by experimentally. Your rate equation may or may not include all the reactant in the stoichiometric rate equation, right? Just now we have seen the iodine was missing, right? Because iodine was 0 order. 0 order, we don't care. Oh, no point writing A the power of 0 is 1. Okay, not? You remember you learned this under indices? Maths. Anything the power of 0 is always 1. 1 times anything is the thing. So we never write 1. Oh, so same idea. That's why you can see 0. Once we know it's 0 order, we just leave it out from the rate equation. No point writing there unless we want to make a point that is 0 order. Oh, so this idea here, 0 order. Okay, right. So your rate equation may include catalyst which does not appear in the stoichiometric equation. So don't be surprised. Once your catalyst is being used, right, it can appear in the rate equations. That is why catalysts speed up rate. Can you see the point now? Can you see the relationship now? Originally, before the factor of your catalyst being added in, your rate equation originally may be carried out without a catalyst. For example, this equation here. You see, you pull all the way up here. This equation here, originally, when the catalyst is not added, right, it is written as rate equals to K concentration of this organic compound. That's it. Before they add in catalyst. After they add in catalyst, right, they did a series of experiments. Experimentally, they determined to be first order. Then they insert in the catalyst. So you can see that in this question itself, right, in this scenario, the concentration of the catalyst do impact the rate. Okay, now let's go back to your O-level days. Remember, you are told what? Catalyst just use small amount. Am I right or not? Small amount will do, right? You did bio before, right? Catalyst you always use in very small quantity. You don't need a lot. Right now, because your chemistry teacher or bio teacher will tell you that it will regenerate itself. Now you think about it. You think about it in the context of example 2. What do you notice? If I really want to speed up the rate of reaction, knowing that I don't have enough of this substance, let's say this one, can I still use very little H plus? No, because the rate equation tell me is first order with respect to H plus. What should I do if I want to increase the rate of reaction? Of course, we know there is a catalyst, so you must understand. First, we know it's a catalyst. The catalyst speed up the rate of reaction. Every one of us know that. But second question here is that, can I increase the concentration of this catalyst? Instead of using 1 mole per dm cube of sulfuric acid, for example, can I use 10 mole of sulfuric acid, per dm cube of sulfuric acid. Yes, because in this question, in this example 2, right, it's very clear that the concentration factor play an important role. When I increase the concentration of my sulfuric acid, the entire reaction, boom, go up 10 times. That is the idea of order of reaction. That is why it's called first order. You increase your concentration by 10 times, your rate also increase by 10 times. Also, again, you rewind what you have learned previously about catalysts. Okay, like iron, Haber process, all those things. Yes, to a certain extent, is yes, but when you come across catalysts, it's not in the solid state. Example, aqueous, right, concentration or H plasma. So you only have concentration factor when you deal with aqueous compound, isn't it? Aqueous substances. Then you got this idea of concentration. Can I use a higher concentration? Or should I follow what we have learned before? Use as little as possible because it's regenerated. By all means, if you really want the reaction to go faster, increase the concentration of your catalyst. You cannot just go by small amount. You can speed up the rate of reaction. But if your job is to go up by 10 times, increase the concentration, no problem. Also try to relate. Sometimes the catalyst play an even bigger role, not just to speed up the rate of reaction, offer the alternative pathway, but itself play an important role in the rate equation. When you increase the concentration over here in example 2 for H+, for example, the rate will tremendously bounce up, boom, all the way up. So good. The catalyst offer a lower pathway. At the same time itself, when its concentration changes, it changes the rate of reaction. That is a double bonus. Fantastic. You go for that, right? Not to increase the rate of reaction. Also rewind what you have learned previously, and then with the information that I share with you today, look at catalysts in the different light, or depending on the nature of this catalyst. Is this just doing a job for lowering activation energy alone, or does it entail more? In this example 2, it is playing a bigger role. It is actually trying to influence the rate of this reaction by its concentration, because it's first order. Whether first order, second order, we don't care. Okay, but this question is first order. So first order means that its concentration will impact the rate. It's not passive, no. It's not just added in a lower activation energy, blah, 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 then speed up the rate of reaction. Itself can also play a role. The concentration itself can also influence the rate. That's why in this example 2 is very fantastic. This catalyst is playing a bigger role than what we expected it to play. Not all the time it will behave this way, but in this example 2, yes. Okay, Hannah. Okay, let's go on to part. This one is done. Okay, now let's go on to point 4. Am I going too fast? You understand the idea of the catalyst? Why is it the catalyst which does not appear in the stoichiometric there? This is the point what I'm trying to say here. So don't be surprised. There are two concepts that whenever we teach this topic, right, students always go away with thinking must be a reactant that can appear in the rate equation. Answer? No. No. You don't appear in the equation, you can still appear in the rate equation. The catalyst, that's all example 2, you can see that the catalyst was not involved in the stoichiometric equation that you formulated, but it appeared in the rate equation. Okay, so you must go away the idea it must appear in the stoichiometric equation, not true. It may include which does not appear. Don't need to appear and don't have to worry about it. Rate equation is rate equation. The balance equation is a balance equation. Don't confuse these two. Okay, set them aside separately and when your treatment, when you look at it. Okay, now let's take a look at zero order. Zero order, you can see this is m equals to 0, rate equals to k. So no matter what happened to this reactant concentration changes, right, the rate is always the same. Okay, independent of the concentration of the reactant. Okay, so no matter you increase concentration by how much, right, the reaction will still happen at a fixed rate. Okay, so you will probably see this rate against 2A. Okay, so this is rate against concentration. Power of 0, that means you are plotting y equals to x, y equals to k, sorry. Y equals to k. Or relate to what you have seen before. Okay, then if you plot concentration against time is a constant gradient. No change. K is a constant. The gradient is k. This gradient is just k. K is always a constant, so therefore you will have your rate as a constant. Change dy dt is a k. Dy dt equals to k all the time. Nothing happened. No matter where you are in the reaction, it is still k. Product against time is the reverse. Same thing. Instead of a curve going up, it is a constant gradient. Okay, increases as constant rate. So very simple. The graph for first zero order is very standard. All straight lines, no curve at all. Okay. Okay, so this is example of zero order. Ammonia to N2 and N3 and 3H2. Okay, so your rate is K. So order reaction, you change your concentration of ammonia, the rate of reaction is still the same. So what does this show us? Ammonia change to your N2 and H2, it is a constant rate. So at a particular temperature, right, your ammonia can break down to form N2 and H2. You don't need to worry about it at a particular temperature. Or do you store inside a cupboard, store inside whatever thing, okay, or put inside special treatment to the ammonia, it will definitely decompose at a fixed rate. Okay, you'll keep decomposing. Okay, so nothing you can do or your concentration, how high, how low, doesn't matter. Okay, so this will decompose to form N2 and H2. So you can see very tough. When Haber produced ammonia, right, he is faced with this reaction, because if you remember, Haber process is a reversible reaction. This reaction is happen even when ammonia is being formed. It's going back, it's going back, it's going back. So he has to struggle with this. I want to produce 1,000 tons. Then at the end of the day, maybe 20% form back into this two again, naturally form back. Also, he has to juggle between the this reaction as well. Okay, right. First order, okay, first order is K, the A and the power of 1. So order of reaction, just like I mentioned, how to derive the units. So units is not fixed. So you must read the question, okay? If the question tell you is rate of reaction is mole per dm³ per minute, this is minute minus 1. Per second, second minus 1. Read the question. Okay, read the question, extract the units used for the rate before you go and calculate the units for the rate constant. You catch the front part, then you can catch the back. Not jump around, then you really, what is this? Okay, then you don't know what is the rate, what is the unit that's being used. Okay, so this is the first order. Rate is directly proportional to the concentration of the reactant. Okay, so this is what your famous curve, y equals to kx. Okay, so now you can plot y equals to kx. So you have your rate against your concentration is a straight line up. You have done this before in maths. The gradient is k. Okay, so you plot A against time downwards. Consider A against time is just like what you shown you earlier, right? So your A decreases, gradient decreases. Okay, so your same thing for here. Your gradient become less steep. Also, this is what you have done. You see, this is more realistic. It's approaching 0. Eventually, will it touch 0? Yes. If all your reactant get used up, eventually you'll touch 0. This point here, because they never extrapolate long enough. But eventually, if this is the limiting reagent, then it touches 0. If it's not the limiting reagent, it will not touch 0. Logical. If it's the limiting reagent, then it will finish up. If it's not the limiting reagent, why would the concentration drop to 0? No way for drop to 0. Okay, so this is a graph. Please take note, MCQ always throw out this kind of graph. They ask you which one is 0 order, which one is second order, which one is first order. You must know what is the y, which one is the x-axis, okay, and then know how the relationship translate into the order of reaction. Okay, so first thing, half-life is very important. This is what you need to remember. Half-life, not half-time. Okay, I ever mark script before student write down halftime. Okay, halftime is when you watch the World Cup or football match, then you got halftime. There's no halftime here in red. Half-life. Okay, so remember T half is half-life. What is half-life? Half-life is half of its original life. Of course, it's half its original concentration. Okay, so it's the time taken for the concentration, the life, so-called the life. Okay, originally your concentration, let's say you have 100 mole per dm cube, drop to 50 mole per dm cube. Okay, fall to original value is called half-life. Okay, first order reaction, right, your half-life is constant at a given temperature. So that is how we tell what is a half-life. Okay, so you can see that from all the other order reaction, half-life is not constant. Okay, so one method you can plot, this is what you always do, this curve here, or the one on top. Okay, usually you can tell from here, let's say you read to half, I put down here. So this one is half A0. Let's say this is A0. This is your first half-life. Okay, then from A0 drop to here. Oh, this is your second half-life. Can you scribble on the notes 1/4 AO? 1/4 AO. Okay, now we look at the product curve. Let's say at the end A0 end up with the endpoint is endpoint here, B0. Okay, I show you the product because I don't know whether you're aware. Half-life is here. B0. Oh, B0 half. Yeah, okay, wait. Let me erase off first. I need more space. Okay. I need more space. Okay, wait. Let me scribble this one down first. Okay, come. I put down lower. Half BO. This is first half-life. T half 1. Same as this. I circle this, I circle this. Okay? Right. Second one is half of this half. Here. Oh, so I want you all to take note of this. Half of this half, not 3/4. Half of this half plus this half. So half of half is 1/4, right? So 1/4 plus the original half is your 3/4. Is it? 1/4 plus 1, yeah, 1/4 like that. This is your second half. Oh, box up. Okay, and so on. Okay, half-life for product is the other way around. Time taken for half the original amount that was formed already to be formed. That's why it's 3/4 BO. Or if the full amount is BO, BO means the final concentration amount of the product. So first half-life is here. Second half-life is time taken for half of this amount formed. This half BO. Half BO is 1/4 BO. So you add up to the original is 3/4 BO. Or this part here you must understand. Because when you look at the product, it's the other way around. Your product is dependent on the reactant. So your reactant drop this way, right? You see, your product also form in this manner upwards. When we see a question later, I will pull out for further discussion. So you all just jot down first, okay, for time being. Okay, any question before we 6:30? Before we end off. I hope I'm not going too fast. Have you all reached this part already, or are you at the tutorial already, or still at lecture? Lecture or first order, second order?
Still having lectures.
Lectures. Have you finished this part? Order of reaction?
Yes.
Okay. So okay. So I'm just behind your lecturer. Rachel, am I behind your lecturer?
Yeah.
Okay, good. I mean, I'm supposed to follow them because if I'm going faster than them, right, that means you have to let me know. Then I have to spend more time to unpack. So trying to bring out certain parts that you all can understand better, huh? Send you Am I
Yeah.
okay
this
behind
one-
your lecturer, right? Your lecturer in front reach all the way to the back end already, Is it towards the end part? I'm still behind them, right?
Almost there.
Almost, okay. So next week you remind me, if I need to slow down certain concept not covered yet in your lecturer, by your lecturer you slow me down so that I can unpack more. Okay, yeah, Rachel, yes?
For the part of 3/4 and a half, I don't really understand.
You see, your total amount when this A0 is a reactant, A0 drop to 0, I call this initial concentration of A. I call it A0. When all the A form the product, I call B0 as a final endpoint. You must understand, it's just like a seesaw. One end must go down, the other end must go up. So when all the reactant reacted, the final amount of product is B0. Can you see a B0 here? This is the total amount of the product that can be formed. Correct or not? You must get this one first, okay? So this one and this one is coincide one. Okay, now we go back to the definition, right? When you drop to half, number 2, half-life, right? Drop to half the amount is also the time taken for half of B to be formed. Correct or not? Half of B to be formed, because the total is B. So half of B to be formed is also the half-life. Now I'm looking from the product end. That's why the curve is going up. Seesaw. You understand? Number 2.
Yeah.
Okay. Number 3, slowly, number 3. Okay, this is number 2, Number 3. Do you agree with me, right? From half AO, drop to half of half AO is 1/4 AO. Number 3.
Yeah.
This is the second half-life. But your product form how much? Your product don't times 2, no, straight away. Your product form half of half BO, which is 3/4 BO, 0.3.
Okay.
So you must understand the relationship between reactant and product. It's just like a seesaw. Reactant go down, product go up. Reactant go down, product go up. The time taken from the reactant to go down by half is also the time for the product to increase by half its original amount. Half its original amount. I don't know whether it's you understand what I'm trying to say, okay?
Yeah.
Okay.
So the step 3 for product is add half of the step 2.
Correct. Because you must still consider the original half, original half that has been formed already. You form 1/4 BO, right? 1/4 BO is half of half BO. You must add to the original amount. That's why it's 3/4 BO.
So the original amount is not number 1 for product, but it's number 2.
The original amount is number 2 that's being formed, correct? Yes, you're right.
Okay.
Yeah, the one is just to coincide with what you have initial and or maybe you're right. So this one this one is actually your 0 point. This one the one, 0 point. When it's all reactant, there's no product, 0 point. Okay, can? All right. If no problem, then next week I see you all. I will end here. Then next week we will carry on with this part. Can? Any problem? If not, then I'll see you all next week. Can?
Okay, thank you.
Let me know, slow me down if let's say I'm going too fast or you need me to unpack certain concept. Okay, but this one we stop at this half-life first. Don't worry. Next week we start from here again one more time. Okay, and I need you all to understand the product one. The product, how the half-life is being built up. Okay, can? Okay, can. Thanks. See you all. Bye-bye. Take care.
Thank you.
Bye-bye.
Thank you.